Hello, today I'm gonna be finding a organic compound with three functional groups. So one of them must contain an oxygen and one of them a nitrogen and the other one's just another functional group. And then I have to name them. So yeah, I got the nitrogen one there, the oxygen. So then okay, so what is it? Then I have to get the electrogeometry and molecular geometry and hybridization. So as you can see here, we have an OH, so hydroxyl group, another hydroxyl group, and then we have a, I'm just pointing it out right now. So so there's the hydroxy, and then the other hydroxy, and then that's a benzene ring, and then that's a nitro group. So yeah, nitro. So essentially benzene is the parent function, like the longest carbon chain in the compound, so that's gonna be the parent function. And then you have to like do the numbering, so clockwise and counterclockwise. So then you have to count where the functional groups are. So it's 1, 3, 5 for both of them. So since they're equal, you're gonna organize it by alphabetical order. So benzene is, as I previously said before, is a parent function that's gonna be at the end. So then for the branches between hydroxy and nitro, hydroxy is, well, the H comes before the N. Therefore, the 1 or 3 are gonna be for both of the hydroxys that are there. So, and the 5 is gonna be for the nitro. So it will be 1. It would be 1 hydroxy, and then it's gonna be 3 hydroxy. And since they are both the same, you can combine it to dihydroxy. So it's gonna be 1, 3 dihydroxy. Let me just move it because I don't have space. It feels like disorganized. So then, yes, it's 1, 3 dihydroxy. I'm not sure if I'm pronouncing it right. But then the only one that is left, it's 5 for the nitro, since that's the one that we chose, the order that we chose. Well, the only one that was able to be there. So then it's 5 nitro. And then we organize this also alphabetically. And we don't count the prefix, the number prefix. So it's going to be 1, 3 dihydroxy. Then -5 nitro benzene. And that would be the name for this whole compound. I'm not sure if we were supposed to do that or only just name the functional groups in the compound, but either way, I guess it's helpful to know how to name a compound, I guess. But I also have to do the electrogeometry and molecular geometry and hybridization for each one of the atoms. So let's see. So I'm just gonna start pointing out the carbons that I'm gonna work with first, and like delete. So I'm deleting like the little numbers that I put before, so we can see the structure of the compound better. But so yeah, so just a little refresher that I was talking about before. Well, I'm not talking about before. I think I don't never mentioned it. But for C, it's carbons are like up to 4 bonds, nitrogen 3 bonds and a lone pair, and then oxygen 2 bonds and 2 lone pairs. And that's like for usual, like cases and like to obey the octet rule. So basically, yeah, like 8 electrons. So each bond has 2 electrons, and while 2 lone pairs has 2 lone pairs will be equal four electrons, or 1 lone pair is 2 electrons. So having that in mind, we can start doing the electron geometry, molecular geometry hybridization. So I'm going to start with the carbons. So we first have to calculate the static number, and I think it's without, I think that's not right. I think it's without the E, yeah. So then you have to add the number of lone pairs plus the atoms, the bonded atoms. Not the bonds, the bonded atoms. So as you can see, like on the carbons, it has one, so it's a double bond, so 2 bonds and 1 bond. But then there's also a hydrogen there, so that's the double bond that I'm talking about, and then 1 bond, so there's 3 bonds. But in order to be the octet rule, it's missing 2 electrons to get to 8. Therefore there's a hydrogen attached there. There's a hydrogen attached there, but attached to like all the carbons there, so it's better for visualization. But essentially it obeys the octet rule, but it's attached to 3 atoms: the hydrogen, the carbon, and the other carbon. So it's gonna be, it has 0 lone pairs, so therefore it's gonna be 0 plus the carbon on top, carbon on the bottom, and the hydrogen. So it's 0 plus 3. Out of it. So yeah, right there. So it gives a static number of 3. So moving on to electron geometry, you need a Vesper table in order to do this, as well as the molecular geometry, and well, the hybridization is something else. But yeah, it's the static number is very important to this part. So for the electron geometry, you go in your Vesper table to static number 3 has 0 lone pairs, and that's gonna be trigonal. So for the electron geometry, it's gonna be 120. So the angle is gonna be 120. And then for molecular geometry is gonna be trigonal planar. And then for hybridization, so to make it like easier to understand, I'm just gonna draw the 1, 2, 3, 4, 5, 6, 7, no, 6, 6 fingers. So then it's gonna be the levels of shells. So then it's S, P, 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 D, and D. I think I did an extra finger. So it's gonna be since static number is 3, you're gonna count to 3 in those fingers. So it's gonna be S, P, and P. Given a result of SP2. But that's essentially for pretty much all the carbons and this compound. So I'm gonna be moving on to the hydroxy. The hydroxy is in the compound. So as I was saying, I'm gonna start doing the hydroxides. So top hydroxide and bottom hydroxide, they're gonna be the same. So looking at the hydroxide, they're attached to the O. So just to make it a little bit better to see, it's gonna be it's the C attached to the O and then the O attached to the H. And then also we have to remember that the oxygen has lone pairs, has two lone pairs, and you count them with the atoms, the what is it, the bonds, and it's gonna be 8. So then you count the number of lone pairs and numbers of bonded atoms, and it's gonna be two bonded atoms plus 2 lone pairs. So that's gonna be equal to a static number of 4. So then going on the electron geometry and the molecular geometry and hybridization, now that we have the static number, but essentially it's from the top and the bottom is going to be the same. It has the same static number for both, the same atoms attached and the same number of lone pairs. So going on the electron geometry, it's going to be static number of 4 and 2 lone pairs. Therefore, that's going to be an electron geometry of less than 109 for the angle. I believe 109. So yeah, it's 4 for static number and then 2 lone pairs. I think so. Yeah, it's gonna be less than 109, and then it's gonna be bent or angular. And then for hybridization, we go again with the hand. That's gonna be 4, so it's gonna be another P, so it's gonna be sp3. So now moving on to the nitro. Hold on. As I was saying before, now we're gonna do the nitro, and just for a little better like understanding and visualization for the nitro functional group, the nitro is attached to 2 O's, and we have to make this fit the octet rule for the elements. So then there's a double bond in 2 lone pairs for oxygen on the right, and then for oxygen on the left is gonna be it's 3 lone pairs. Yes, it's 3 lone pairs. But I'm not sure if yes, it's 3 lone pairs, and then a negative charge and just 1 singular bond, and then nitrogen is gonna be positive, and this is due to how oxygen is more electronegative than the nitrogen, so therefore it's gonna take the lone pairs and just obey the octet rule. And it's gonna be more stable overall, so that's why it has the negative charge. And also we have to take into mind that the nitrogen is attached to carbon, but that's gonna be specifically for the electron geometry static number molecular geometry for the nitrogen. So then, and now we're gonna go and choose one of the oxygens. So I'm gonna start with, I believe, the the left oxygen. So the static number is going to be 1, 2, 3 lone pairs plus 1 atom attached. So that's going to be 4. So the electron geometry, you go on your Vesper table to like find electron geometry, molecular geometry. You go on your Vesper table, and essentially on static number 4 and 3 lone pairs. Where is it? 3 lone pairs, and that's gonna give you linear. That's for the molecular geometry. The electron geometry is gonna be 180 for the angle. So this is kind of lagging. So 180 there, and then linear. And then for the hybridization, we go again with the finger. It's gonna be 4. So it's gonna be again with the same of the hydroxy. Hydroxy is gonna be sp3. So now moving on to the oxygen on the right, we calculate the static number, and that's as you can see, that oxygen on the right has 2 lone pairs, and it's bonded to 1 atom. So it's going to be 2 plus 1. It's going to be 3. The static number is 3. So then for the electron geometry, molecular geometry, so electron geometry is going to be static number 3 with, 2 lone pairs. So you go again on your Vesper table. And that's gonna result on again a 180 angle, and then it's well, I had to cut the video because my brother started to sing, but yeah, the molecular geometry will be linear, the electron geometry will be 180 for the angle, then hybridization, since it's 3, is gonna be sp2. So again with the fingers, so SPP is going to be SP2. So now the only one that is left is nitrogen. So the static number for nitrogen, so it is attached to 3 atoms, and it has no lone pairs in this case. So therefore, it's going to be, so for the static number is going to be 3. So 0, so it's going to be 0 plus 3 equals 3. Since it's kind of laggy, so 3. And then for electron geometry, you go on the Vesper table. 0 lone pairs 3 is going to be 120, and then trigonal planar, and the hybridization, we go again with little fingers, and that's gonna be 3 sp2. So sp2. So I believe that's it for all of it. So I named the functional groups. I wasn't sure if we had to name the whole compound or like explain how to name it, but so I did it, but I also did the electron geometry, molecular geometry and hybridization for all the atoms in the compound except hydrogen. Essentially all the carbons are the same, hydroxide are the same, the oxygens on the nitro are different, and of course the N for the nitro functional group is different as well. But I believe that's it for this video. Thank you.